directly proportional to the position of the bulb along the length of the rotameter. And so this is something that we had seen yesterday. So today I would talk about few other methods of flow rate measurement. We'll start with pitot tube, pitot static tube. We'll also talk about cases where flow becomes compressible, typically for high Mach number flows. And then we would talk about the hardware anemometer. So first of all, what is a pitot tube? Pitot tube is shown here. Give me a second. So pitot tube is shown here. This is typically a tube of small diameter. The diameter of this tube is small compared to the tube or the duct in which we are trying to measure the flow rate, so that the insertion of the pitot tube doesn't appreciably modify the original flow field inside the duct or the tube. So it sort of becomes still a non-intrusive method as much as possible. So this is a tube with a rounded nose, okay? And this rounded nose is to ensure that there is no flow separation or formation of vortices. Flow just goes past this pitot tube smoothly. It just gives a streamlined shape to the tube. And this pitot tube is actually connected to one end of this manometer. And at the other end of the manometer, you have a static pressure tab. Okay. So when flow happens, there is no flow in the perpendicular direction, right? So that means whatever the pressure that is there on this limb of the manometer is in fact the static pressure in the tube at that point. Whereas the pressure on the right limb of the manometer, which is connected to the pitot tube, this actually measures the stagnation pressure, because when the fluid goes past this pitot tube at the nose, the fluid molecules come to complete rest, converting the entire kinetic energy into pressure energy. So the stagnation pressure is basically the sum of static pressure plus the dynamic pressure. As you can see here, P naught indicates the stagnation pressure, which is equal to the static pressure plus the dynamic pressure, which is half into rho into V square. So this is basically how you can relate stagnation pressure to static pressure by adding static to dynamic pressure. Now, in a manometer, the difference between the stagnation pressure, which is on the pitot tube side, and the static pressure, which is on the static pressure tab side, this difference is basically given by the change in the height of this manometer liquid. So P naught minus P is given as the density of the manometer liquid minus the density of this fluid flowing through the tube into G into H. Okay. And now if we substitute rho m minus rho into GH here in this equation, we can actually find the flow velocity in this way. So flow velocity will be 2 into rho m minus rho into G into H divided by rho whole square root. So this is basically giving you the flow velocity. But knowing the flow velocity and knowing the cross-sectional area of the tube or the duct, one can accurately sort of predict what is the flow rate through the tube or the duct. Now this way of velocity measurement has application in measuring velocity of aircraft, where in a typical aircraft, the stagnation pressure is measured using a pitot tube, typically placed on a wing. So if it is placed on a wing, then the flow is actually seeing the leading edge of the wing, right? So there the flow would come to the rest and converting the kinetic energy into pressure energy. So at the leading edge of the wing, where these typical stagnation pressure probes are placed, you would end up measuring the stagnation pressure. Whereas the static pressure tap can be perpendicular to the fuselage. So there is no flow that is perpendicular to the fuselage when the aircraft is cruising. So this pressure on the pressure probe on the fuselage, which is held perpendicular to the fuselage body, gives the static pressure, right? So the probe at over the wing gives you the stagnation pressure. The port on the fuselage gives you static pressure. So by measuring the difference, you can actually predict what is the velocity of the aircraft. This pitot static tube would, so you have pitot tube, okay, this is pitot tube, and this is static pressure tab. One measures stagnation pressure, one measures static pressure, and difference between the two gives you dynamic pressure. From there, you predict the velocity. Now, these two features can be combined into a single tube, which is called pitot static tube. And pitot static tube would sense both the stagnation pressure as well as the static pressure on the same device. So this is a typical construction of pitot static tube. Okay, you have a sort of streamlined nodes, and here at the tip of the nose, you will have a stagnation point. That means this area, it is connected to one UT manometer, would measure the stagnation pressure. Whereas we make a hole here, static pressure holes, which is can be connected to basically the outer tube, which is connected through this outlet to another manometer. So essentially, you are measuring the static pressure, you are also measuring the dynamic pressure, the stagnation pressure. And the difference between the stagnation pressure and the static pressure gives the stagnation pressure. The stagnation pressure is a function of density and velocity. From there, we actually predict what is the velocity. Now, this arrangement and this theory works fine when the flow is incompressible. When the flow is incompressible, that means the Mach number is less than 0.3. Now, in situations where the flow is subsonic, that means Mach number is less than 1, but Mach number is greater than 0.3. So in this range, although it is subsonic flow, the density variations are going to be significant. And there are relations from gas dynamics which can be used to relate the pressures in such kind of compressible flow. So the process of stagnation, where, as I said, at the leading edge of the pitot tube, you would have a stagnation point. So basically, the entire the conversion of the dynamic pressure and the static pressure into stagnation pressure is governed by the thermodynamics of compressible flows. And it is this compression process is taken to be an isentropic process, meaning the entropy during the process of stagnation, where the fluid molecules slowly come to rest, is said to be isentropic. And from gas dynamics, considering the process to be isentropic, we can actually show that the ratio of the stagnation pressure to the static pressure is given by this expression, which is 1 plus gamma minus 1 by 2 into m squared to the power gamma over gamma minus 1. And this is gamma is basically the ratio of specific heat, Cp over Cv, and the m is the Mach number, okay, which is the ratio of the speed of a body or a fluid to the speed of sound in that medium. And from here, you can actually do a simple thing. -1 you add on the left hand side and -1 you add on the right hand side. So you get P naught divided by P minus 1, which will be P naught minus P. And the denominator P is multiplied on the right hand side, which is P into 1 plus gamma minus 1 by 2 m square to the power gamma by gamma minus 1. And again, we have -1 because of this minus P. So this pressure difference should appear in the manometer measurement, where we said that the P naught over P is, so here you basically have -1, and then so that should be equal to rho m in the manometric liquid, rho m minus rho into GH. So basically from here, you could actually show that m from here, m will be equal to basically here, if you want to find out m, you have to take first P naught, P into the right hand side, and then it would become 2 by gamma minus 1 into 1 plus rho m minus rho divided by P into G into H to the power gamma minus 1 over gamma. So this is what you want to find from this expression, which is given as this. Now, this pressure ratio P naught over P is actually a function of Mach number. And you can see that x-axis you have the Mach number, and y-axis you have the pressure ratio. And you can see that both for compressible and incompressible fluids, the pressure ratio values are identical until a Mach number of 0.3, where we know that above 0.3 flow becomes incompressible. So that means whether you use compressible assumption or incompressible assumption to find the velocity using a probe, you will have the same answer as long as Mach number is less than 0.3. But above 0.3, there is some deviation between the case, the actual case, which is, you have the compressible flow, and this is basically the incompressible flow. There is a difference above a Mach number of 0.3. So the incompressible assumption is all right for Mach number about 0.3. So you can see here, this is Mach number, and this is the percentage change in the pressure ratio. So you can very well see until about Mach number of 0.3, this percentage change in the ratio is very close to 0. Now, starting with this expression for pressure ratio P naught by P equal to 1 plus gamma by minus 1 by 2 into m square to the raised gamma over gamma minus 1, this compressible relation, we can show that in situations where P naught minus P is very negligible, this equation really reduces to the famous Bernoulli equation, okay, which is applicable to only incompressible flows. So you start with this incompressible assumption expression, and you assume that you know you assume that when the flow becomes incompressible, you can recover the Bernoulli equation, which is valid for incompressible flow. So I'll just take you through the math here. So P naught over P is 1 plus gamma minus 1 by 2 n square to the raise gamma divided by gamma minus 1. So this comes from gas dynamics, stagnation pressure to static pressure relation in case of a compressible fluid, where Mach number is between 0.3 to 1. It's compressible, but Mach number is subsonic. It is not supersonic. If it is supersonic flow, then you have another relation for the stagnation to static pressure. So if you adjust this, you can very well find m square, which is P naught divided by P to the raise gamma minus 1 to the power gamma. Then this one goes there, become minus 1. And the whole multiplied by 2 by gamma minus 1. So this is basically your m square. Now, let's say the difference between the stagnation pressure and static pressure is not very large. Okay. Then we can actually write from here is that just adjusting, dividing by P. So P naught minus P naught by P. So this will be equal to P by P 1. So this will go to the other side, and that will become 1 plus dP over P. Now, if you assume flow to be incompressible, then delta P is less than P, right? Now, the question is, under that assumption, whether this equation, which is derived for compressible flows, you recover the incompressible flow equation, which is the Bernoulli equation. So when delta P less than P, so P naught by P you have found here, just substitute here. So that will be P naught over P into gamma minus 1 by gamma, which will be equal to here 1 plus delta P by P whole to the power gamma minus 1 by gamma. Now, here you can see that m square is given as 2 by gamma minus 1 into this ratio minus 1. So you substitute for this ratio P naught by P from here. So when you substitute, you get m square will be equal to 2 by gamma minus 1 plus into 1 plus gamma minus 1 divided by gamma in delta P by P minus 1. So this is minus 1. So this minus 1 will get cancelled. Gamma minus 1 gamma will get cancelled. So you have 2 by gamma into delta P by rho. That is equal to P by A whole square. Okay. So your speed of sound square from thermodynamics is gamma into pressure by density, gamma P by rho. And now, if I substitute for A square here, gamma P by rho, you can show that the Mach number or the corresponding velocity can be expressed as 2 into delta P over rho square root. This is nothing but the Bernoulli equation, because what is this? If you expand, this will give you, let's say, you square both sides, V square divided by 2. Then we have 2 into delta P by rho square root. And this is basically the Bernoulli equation, because if you take V square, so this will be V square by 2 and plus delta P by rho will be constant, and which is basically essentially the Bernoulli equation. Now, let us talk about a proof like a pitot tube when the flow is supersonic. So this will be again relevant to aircraft or some other kind of spacecraft, which is moving through, or maybe submarine, which is moving at very high Mach number. Okay, Mach number that are greater than 1. And this class of fluid flows are called supersonic flow. And in this particular case, as you would see, that if this is the probe, we expect a stagnation point to be formed at the end, at the tip of this structure, this probe. And this is basically, let's call it as stagnation point, and which is PO2. Now, in case of a probe, something like this, when Mach number is greater than 1, we actually have a shock wave, which is curved in nature. And what is a shock wave? Shock wave is basically a line in a compressible flow about which there is a sudden change in the property. Density will change suddenly, velocity will change suddenly, properties will change suddenly about that line. And that is known as your shock wave. Now, in case of Mach number greater than 1, in front of a pitot tube or any other kind of instrument, your shock wave is in the form of a bow, and that is why it is known as bow shock. So what happens across the shape? You basically have on the left side of the shock, the Mach number is greater than 1, and the pressure is P1. Just right across the shock wave, the Mach number actually reduces from greater than 1 to less than 1. So on the right side, the Mach number is less than 1, and consequently, the pressure is also different. So that means you see that across this line, you have a sudden change in the property, both velocity and pressure. And this is basically the bow shock that we just spoke about. And from gas dynamics, the ratio between the stagnation point pressure, PO2, to the static pressure on the approaching flow has been given. So this is something that is available from gas dynamics. Okay, we are not talking about the derivation of it. We just are talking about this from the gas dynamics. So the stagnation pressure to static pressure ratio is given as 2 gamma into Mach number square divided by gamma plus 1 into 1 plus gamma minus 1 by 2 into 1 plus gamma minus 1 by 2 m1 square divided by gamma m1 square plus gamma minus 1 by 2 whole to the power gamma by gamma minus 1. So this is the stagnation pressure to static pressure in case of a bow shock. And basically, if you can measure the stagnation pressure, which is, let's say, using some instrument, both stagnation pressure and the upstream pressure P1, then we would be able to predict what is M1. And if we know M1, we can say what is V1. That means what is the velocity of the fluid. Okay, so that is how one predicts velocity inside a fluid using an impact probe, which is working in a supersonic flow. And here you can see that we have Mach number in the x-axis, y-axis we have pressure ratio of the pressure of the static pressure to the stagnation pressure. And as you can see that stagnation pressure comprises of static pressure plus dynamic pressure. And since you will be able to measure these two pressures, we can then plot how the pressure ratio varies with Mach number and compare it with the experimental values. And you can see that as Mach number increases, since the dynamic pressure becomes stronger and stronger, the stagnation pressure here increases because of the increase in velocity. So the ratio actually decreases. The static to stagnation pressure actually decreases. Now, what if the probe is in the shape of a wedge? Okay, not like a well-rounded shape that we just spoke in the previous slide. Not like this, but it's a very sharp, there's a very sharp edge, something like this. Now, from gas dynamics, it is understood that when you have Mach number greater than 1, that means you have supersonic speed. In case of a wedge-shaped object, you would encounter what is called an oblique shock. The shock would be straight, but at an angle with the flow direction. Okay, so this the shock wave is called oblique shock because this is at an angle. So again, from gas dynamics, there is ratio of the downstream pressure P2 to the upstream pressure P1 is given in the literature. This is derived in the literature, which is given as 2 gamma plus 1 into m1 square sine square alpha minus gamma minus 1 over gamma plus 1. So if you are dealing with such high speed over a probe, and you want to sort of measure the pressure here downstream by, let's say, creating a hole on the wedge, say probe, so that there is no flow in the perpendicular direction, right? So if you create an opening, there is no flow in this direction, but the shear that is happening closer to the boundary would give rise to some kind of pressure, that is static pressure. The same can happen for the stagnation region P1. So if you know P2 and if you know P1, then you can predict what is the Mach number M1, that formula.
Sir, just one query.
Yeah.
Here the statement says that some distance away from the apex, right? So that means I cannot have it very close to the point of the wedge.
So basically it's saying that you do not have it right here, okay, because that is passing through the shock wave. So you may have an opening somewhere here or maybe here. Some distance.
So it is not predefined, like this is how much it should be.
It is not predefined. You can have it, but not right at the apex. Okay. It says that it is some distance away from the apex. This is the apex where the shock wave is passing through that. So shock wave is a discontinuity in the flow field, right?
So the discontinuity in the flow field will not depend upon where I am measuring, that means.
Yeah, this discontinuity will always exist. And in this case, unfortunately, this discontinuity is passing through the apex. So that means if you want to measure P2, you would basically measure somewhere else downstream, not right at the apex. Okay. So
yeah, okay, sir.
P1 you can measure because this is in the free stream, I mean incoming stream. So you can put in a pitot tube and you can measure what is P1. Measuring P2, you basically do using, this pitot tube can be integrated with the surface of the probe. So you use that to measure P2. Okay, so once you know P2 and P1, you know alpha, and this alpha is basically the shock angle, and gamma is Cp by Cp. So if you know P2 over P1 and you know alpha, gamma, then you can actually predict what is the velocity of the flow, M1. Okay. So in addition to, yeah.
Just want to know how we can measure that oblique angle.
So typically this oblique angle is also fixed, alpha. I have not mentioned the value here, but depending on the range of Mach number, okay, alpha has a fixed value. It is typically between 15 degree to 20 degree, okay. And of course it varies. If you know, okay, whether you are expecting the Mach number of between 1 to 2, or you are expecting Mach number of 5, this alpha will slightly vary, but it is typically between 15 to 20 degrees. So alpha has a fixed value for a Mach number. So this is known from experiment. People have done experiments for different phase angle. This alpha would vary, but it is a function of Mach number for a given phase angle. So these are available in the literature. So if you can just measure the pressure and you know the Cp by Cv ratio, you should be able to predict what is the Mach number and consequently the flow velocity.
Okay, sir. Thank you.
Now, in addition to pitot tube and pitot static tube way of measuring velocity and from velocity deriving the flow rate, another instrument which can be used for measuring flow rate is called hot wire anemometer. Okay. So hot wire anemometer, a typical construction of a hot wire anemometer is shown here. So this is basically some kind of structure. This is mostly for support. So you have, again, on this bigger support, you have the shaped support, and which is holding this very thin tungsten wire. Okay, so these are the ends of the tungsten wire, which is typically coated by copper, because this copper can then be integrated with some kind of Wheatstone bridge circuit. So you can have electrical connection going from this copper ends. So basically this tungsten wire is used as a resistor in the Wheatstone bridge circuit. Okay. So this is the typically the diameter of this tungsten wire will be few hundreds of microns to tens of micron. Very thin, because as you know, the resistance of a wire is inversely proportional to the area of cross section. Okay, so area of cross section is very small. That means the resistance is very high. And why we need high resistance here? Because this principle that we will just subsequently see is based on the resistive heating, I square RT, which is the resistive heating. The R has to be appreciable. It has to be high so that there is good amount of heat that is being generated. So that is why we need a very high resistant wire, and the resistance of the wire can be increased by making it thinner and thinner. So typically, as I said, it is tens of micron to hundreds of microns, and the length of this wire is few millimeters, okay, maybe 2 to 3 millimeters. And the entire structure, as you see, including the shaped support, is about 5 to 10 millimeters. Okay, so this is basically exposed to the flow. Okay, flow is happening over this tungsten wire, which is a cylindrical wire, typically a cylindrical wire. So the principle is that when current is passing through this wire, it is getting heated up. Now, faster is the flow, faster will be the heat lost from this wire, right? It is quite intuitive to think that if you blow air over a hot surface faster, then it is going to cool faster, or it is going to release more and more heat faster, right? So this is the principle, okay? So that velocity information that you need to know what is the flow is basically converted into some kind of thermal effects in terms of the heat exchange from the wire into the surrounding. Okay. So either there is a large heat dissipation when you have a flow, and that is because of the first, when you have a large amount of velocity or higher velocity, there is going to be sort of a cooling effect that develops here if the current is constant. Okay, so that means if the current is constant, it is going to lose more and more heat, and the resistance is going to change. Or you can say, I want to hold it at a constant temperature. So if you are holding at a constant temperature and the heat is being lost, that means you need to supply more and more current. So this hot wire can operate in two modes. Okay, constant current mode, constant temperature mode. This is something that we will see subsequently. But let us look at the thermal analysis of this heated wire. Okay, so as we said, the resistance of the wire is a function of temperature. This is something we know when we talked about RTDs, that resistance of metals is a function of temperature. So that means you can expect that resistance of the wire at a particular temperature TW is RW, which is R infinity into 1 plus alpha, which is the temperature coefficient, into TW minus T infinity. Here, infinity refers to a reference state. It could be just ambient temperature and the corresponding resistance at ambient temperature, or any other reference state depending on your convenience. And TW is basically the wire at a particular temperature, and at that temperature the resistance will be RW. Okay. And for if you have a platinum wire, then you would have the temperature coefficient something like 3.5 × 10⁻³ per degree C. And if you have a tungsten wire, accordingly, you will have the temperature coefficient alpha. So alpha is known for a given material. So the heat that is dissipated by a hot wire, the cylindrical wire, is given by the square of the current passing through the wire into the resistance of the wire, I square into RW. Now, as I said, this wire is a cylindrical surface. So when there is flow over the cylinder, there is loss of heat. And this loss of heat is through convection, which is given by the surface area of the cylinder, which is typically pi into D into L. Okay. This is the surface area of the cylinder. So it is like the surface area into H. H is basically the heat transfer coefficient. Okay. H into A into temperature of the wire minus the ambient temperature. So this is the rate at which heat is lost from the wire. So these two have to be equal. Okay. The rate of heat generation should be equal to the heat loss from the wire. So when you equate these two, now this heat transfer coefficient, how do we express the heat transfer coefficient? Because till now we do not have the velocity information here. None of the terms involve velocity. The only term which is a function of velocity is the heat transfer coefficient. The heat transfer coefficient is higher when your flow velocity is higher. Okay. So that means that will give rise to faster and faster cooling or higher heat transfer exchange. So there is this relation given by King's. It is known as King's law. And this is valid for a hot wire cylinder in cross flow. Right? So this is like a cross flow situation. The cylinder axis is in this direction. Flow is happening in this direction. So in this kind of cross flow, this King's law is valid, which says that pi d into L into H is basically can be expressed in this form. A plus B into velocity to the power n, where A and B and n are basically constants that can be determined through proper calibration. But what is important to note here is that D and L are geometrical parameters. So you said that heat transfer coefficient is basically a function of velocity. Okay. So now we go further. From the previous slide, we have a resistance of the wire, which is R infinity into 1 plus alpha into TW minus T infinity. So basically, TW minus T infinity is basically RW minus R infinity divided by alpha into R infinity. So now going back here, I square RW. So in place of pi d into L into H, you substitute A plus B into V to the power n. And in place of TW minus T infinity, you express the resistance of the wire, RW minus R infinity divided by alpha R infinity. Okay. So now if you rearrange this equation, you can write that A plus B into V to the power n, because velocity is something that you want to determine. So you can write A plus B into V to the power n will be equal to the remaining term, which is I square RW alpha R infinity divided by RW minus R infinity. So this equation is called the basic hot wire anemometer equation. And starting from this basic hot wire anemometer equation, we can actually analyze two different types of hot wire probes. One operating at a constant temperature, which is known as constant temperature anemometer. And the other one is called constant current anemometer, which is called CC anemometer. So I would stop here just in case if you have any question, but tomorrow we're going to look at the constant temperature anemometer, how they work. And when we, in a constant temperature anemometer, we will ensure that the temperature of that wire, tungsten wire or the platinum wire is kept constant. And we see that in order to keep the temperature constant, we have to vary some kind of resistance in this Histon-bridge circuit. And through adjustment, we can ensure a constant temperature. And from there, you can actually sort of see the constant, the governing equations which governs the constant temperature anemometer, how the output actually can be correlated with the input, which is the velocity. And you can typically see a nonlinear relation, and how by taking logarithmic, you can have a linear relation between the output and input. So this is something we will see tomorrow, but let me stop here. If you have any question, we can discuss.
Recording stopped.
So anyone has any question on this lecture?
Sir,
Yeah.
So for this hot wire anemometer, if we are measuring flow or velocity of hot gases itself,
Yeah.
how this relates in that case?
So
So if the input flow is itself having higher temperature
higher
or
temperature, yes.
Yes, sir.
So that is a good question. So you can see that heat transfer can happen in both ways. Okay. So the heat, when it flows into the wire, okay, the wire temperature, let's say the ambient is hot and wire is cool. Okay. So now the heat exchange will come from ambient to the wire. So in this case, let's say if you are trying to maintain a constant temperature, since the heat energy is coming into the wire, you would see that you have to reduce the resistance of this circuit. Okay, basically the control becomes the reverse when the heat flow is into the wire versus in a situation where the ambient is cooler and the wire is hotter. But this principle is applicable to both when the wire is hotter or the ambient disorder. So you can see here. So when TW is less than T infinity, this term becomes negative, right? So basically resistance of the wire becomes smaller than the resistance of the wire at the native condition. Okay. So the consequence will be that you have to have the, in case of constant temperature anemometer, you have to flip the direction in which you want to change the shunt resistance. And similarly, in case of a constant current, you would see that the variable resistance has to be reversed to ensure that the current that is flowing through the hot wire probe is same. But you can do both. Both hot fluid and cold fluid velocity measurement can be done using hot wire.
Okay, thank you, sir. Thank you.
Sir, I just have a small request, if it's possible.
Yeah.
Can you actually help us with solving the midterm question paper that we had? So if we can actually have a class.
We will do that. As I said, let me finish this pressure measurement, flow.
Sure.
Okay. And then we will, have one class where I can solve this as well. And
Yes, sir.
there is another requirement to go over the basics and so on. So we will take care of these one by one.
Sure. Thank you.
Okay. If there is no further question, then thank you all, and we will meet again tomorrow.
Sir, Professor. Hello.
Yeah.
Sir, tomorrow 5 to 6 you are available, then we can have a class, sir. Yes, tomorrow's Mani sir is not taking the class.
Oh, okay. So just give me a second. I will tell you. You were saying 5, right?
Yeah.
Yeah. So we can have the class at 5.
Thank you, sir.
So I think the code office can note it, and maybe 5 o'clock we need to start the class.
Sure, sir. So we will be there available, sir, to 5 o'clock.
Same link, na?
Yeah. So please send an email to code office so that they are also aware of.
Okay, sir. Okay. I will send, sir.
Okay. Thank you.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.